I'm going to explain the Heisenberg uncertainty principle. The basis of it is that there is a limit to how accurately we can know both the position and momentum of a particle at any given time. The mathematical form of the uncertainty principle states that delta x, which is the uncertainty of the position of the particle along some direction, times delta p sub x, which is the uncertainty of the momentum of the particle along that same direction, has to be greater than or equal to Planck's constant, h, divided by 4 pi. Position is self-explanatory, while momentum is a measure of where the particle is going. So, at the extreme ends of this principle, if we know exactly where a particle is, we have no idea where it is going, and vice versa. Note that in three-dimensional space, we have a coordinate system with 3 axes, x, y, and z. There's an equivalent uncertainty principle for each direction. Now, while there is a relation between position and momentum in a given direction, there is no relation between different directions. I.e., I can know the exact position in the y direction and the exact momentum in the z direction, and that would not violate the Heisenberg uncertainty principle. Throughout the course of this video, I will focus exclusively on the x-axis, however. I just want you to be aware that everything I say applies to the y and z axes as well. There is also an uncertainty principle for time and energy. However, to cut down on confusion, I will address this version later. Now, one last thing I will mention in this segment is that the Heisenberg uncertainty principle is commonly written as delta x times delta p sub x has to be greater than or equal to h bar over 2. In this case, h bar is just shorthand for h, which again is Planck's constant, divided by 2 pi. I don't particularly like this form, so I will stick with the original one I mentioned. I just wanted you to be aware of this other format. Now, based on that last segment, you may be thinking, hey, wait. I can measure the position and momentum of a particle, such as say a baseball, with complete accuracy. It is entirely possible to know both of these quantities almost exactly. Now, the confusion on this is quite justified, because the Heisenberg uncertainty principle is a quantum mechanical phenomenon, so it only occurs for very small masses. To demonstrate this, we're going to calculate the uncertainty in position for both a baseball and an electron, given the uncertainty in momentum. Starting with the baseball, let's say it has a mass of 1 kilogram, is traveling at 30 meters per second, and we know the speed to within 0.1%. Since momentum is just mass times velocity, we get a momentum of 300 kilogram meters per second. The error in this is just a momentum times the accuracy of our measurement, that is 300 times 0.001, which is 0.3. We then move the uncertainty of momentum over to the other side and use it to calculate the uncertainty in position. Using the value 6.626 times 10 to the negative 34th for h, and dividing it by 4 times pi times 0.3, we get a value of 1.758 times 10 to the negative 34th. This is the minimum uncertainty that must exist for determining position. This uncertainty is almost 20 orders of magnitude smaller than the size of a nucleus. An accuracy that high is well outside the realm of current technology, so for a particle as massive as a baseball, the uncertainty principle is negligible. The story is different, however, when we look at the electron. In this case, let's say the electron is traveling at 300 meters per second, but we still know the speed to within 1.0%. An electron has a mass of 9.109 times 10 to the negative 31st kilograms. Multiplying it out, we see that our electron has a momentum of 2.733 times 10 to the negative 28th kilogram meters per second. Our uncertainty in momentum is thus 2.733 times 10 to the negative 31st. Using the same value for Planck's constant, 6.626 times 10 to the negative 34th, and dividing it out by 4 times pi times our uncertainty and momentum, we get 1.93 times 10 to the negative 34th. This is our uncertainty in position, which is about 1/5 of a millimeter. This may seem small, but it is actually 12 orders of magnitude bigger than the size of an electron. So we really don't know where the electron is. This is the trade-off of the uncertainty principle. If we know the momentum of something fairly accurately, the position is almost impossible to determine. However, as this example just showed, this only applies to particles of small masses. The Heisenberg principle is undetectable at large scales. This is why you don't notice it when doing position and momentum calculations for everyday objects. Now that I've explained the general principles of the Heisenberg uncertainty principle, I should explain what causes it. The quick answer is that it is caused by the measurement of the objects. We see things using light. As such, if you want to see something, light has to bounce off of it. The same thing is true if we want to measure something. Light has to bounce off of it. Unfortunately, light has momentum, which can disturb our particles as we measure them. Now, at large scales, this momentum is negligible. You can't move a baseball with a laser. That's just not how that works. However, at small scales, say around the size of an electron, the momentum of light has a large effect. Let's say we want to measure the position of an electron. To disturb it as little as possible, we bounce 1 photon off of it. Well, now we know where the electron is, but since the photon exchanged some of its momentum with the electron, we now have no clue as to where the electron is going. This is the basis of the uncertainty principle. A good analogy I heard for this is that determining the position of an electron with light, which is the only way to measure it, is like determining the position of a basketball by throwing other basketballs at it. You are limited in how much information you can gather by the mere nature of measuring. It's at this point that I can provide a good explanation for the energy form of the Heisenberg uncertainty principle. When energy is emitted, it does not leave all at once, but rather leaves over a period of time. The length of time that we measure the emission is proportional to the amount of energy that we observe leaving. This time interval, where we measure the object, is the uncertainty in time. The longer this time interval, the more sure we are of how much energy leaves. The sureness of how much energy is emitted is measured by the uncertainty in energy. These two quantities, time interval of measurement and sureness of the energy, are related by the Heisenberg uncertainty principle. Mathematically, this is represented by delta t, the uncertainty in time, times delta E, the uncertainty in energy, has to be greater than or equal to Planck's constant, h, divided by 4 pi. An example to help explain this would be that if we only measure the emission for a few nanoseconds, we only get a very brief glimpse at the energy leaving. So, while the time interval is very short, and thus we are very sure of when the energy is emitted, we have no real idea as to how much energy is emitted. This version of the uncertainty principle is based on the fact that any measurement we make takes a certain amount of time. Lastly, I would like to derive the uncertainty principle, so you know where it comes from. However, before I do that, I need to talk a bit about wave-particle duality. I won't go super in-depth, because this topic could be a video on its own. However, as I have mentioned in my light video, electromagnetic radiation, which was traditionally thought of as a wave, is also a particle. Light waves have both momentum and energy, quantities typically associated with particles. You can calculate the momentum from the equation P equals Planck's constant divided by the wavelength lambda. Likewise, energy, E, is equal to Planck's constant times the frequency, nu. Now, just as with light, which was traditionally thought of as a wave, that has also been shown to exhibit particle properties, electrons, which are traditionally thought of as particles, also exhibit wave properties. In fact, this wave-particle duality is true of all particles. It is not noticeable at large, everyday scales for the same reason the Heisenberg uncertainty principle is not noticeable at large scales. Everyday objects are massive. So, just as you don't notice the uncertainty in position for a baseball because the uncertainty is so small, you don't notice the wave nature of a baseball because the wavelength is so small. That being said, small-scale particles have especially noticeable wave properties. Most prominent of this is that they experience diffraction effects, a behavior only accomplished by waves. You can calculate the wavelength and frequency of electrons and other particles using the same equations to calculate momentum and energy of light. P equals h divided by lambda, and E equals h times nu. Note that while the wavelength, lambda, times the frequency, nu, still gives you the velocity of the particle, this velocity is not the speed of light. Only light can travel at the speed of light, c, because it is massless. Particles, which have mass, must travel slower. As such, wavelength does not depend on frequency for particles. Now that I've established that particles are also waves, we can derive the Heisenberg uncertainty principle. Since particles are waves, they can do anything a wave can do, including constructively and destructively interfere. This just means that when two waves overlap, you add their amplitudes to form a new wave. So, if you have two identical waves that are in phase, which means the peaks are at the same location, the amplitude of this new wave will double. However, if these same two waves are 180 degrees out of phase, meaning the peak of one is over the trough of the other, the waves will exactly cancel out, giving you zero amplitude for the new wave. This is for identical waves. However, if you have two waves that interfere with slightly different wavelengths and frequencies, you get an oscillating pattern like this. The new wave has an amplitude that varies in magnitude with position. This is the same type of wave you get from sound, since sound is just a bunch of different waves added together. The new wave will reach its maximum amplitude periodically, whenever the peaks of the two base waves become in sync again. We have observed what happens if we add together two waves of slightly different wavelength. But what happens if we add more than two waves, all with slightly different wavelengths? For each of these waves that we are adding, their wavelengths fall into a range of delta 1 over lambda. This is just the reciprocal of the smallest wavelength minus the reciprocal of the largest wavelength. By adding more waves, it takes a longer time for the peaks to all come back in sync. This means that the distance between maximum amplitudes of the new wave will increase. If we add together an infinite number of waves, the distance between the maximum amplitude of the new wave will be infinite, which is to say that there will be only one maximum amplitude for this new wave. This is because the peaks never come back in sync, and after a certain distance, delta x, the arrangement of amplitudes just becomes random, forever canceling out to nothing. Note that although we are adding together an infinite number of waves, all with different wavelengths, they still all fall within the range delta 1 over lambda. This is accomplished by having infinitesimally small changes in the wavelength. For example, say we have light waves from 400 nanometers to 700 nanometers. This is only a range of 300 nanometers, but we can fit an infinite amount of waves in there if the wavelengths of each wave only change by a very small amount. Think of it like integrals from calculus, and all the little rectangles that are formed to add up to the area of a curve. Now the range of wavelengths we have, delta 1 over lambda, is related to the size of the bulge, delta x, for the new wave. the larger the range of wavelengths, the shorter the length delta x of the bulge. This is because the larger the number of wavelengths available, the faster they cancel each other out. In fact, using mathematics that are beyond my understanding at least, we can show that the range in wavelengths, delta 1 over lambda, times the size of the bulge, delta x, has to be greater than or equal to 1 over 4 pi. If we then multiply both sides by Planck's constant, h, and use our equation for momentum of a wave, we see that delta x times delta p sub x for momentum is greater than or equal to Planck's constant divided by 4 pi, which is Heisenberg's uncertainty principle. There is a similar relationship between length of time, delta t, and range of frequencies, delta nu. Multiplying this by h and using our energy equation, we see that delta t times delta E for energy is greater than or equal to Planck's constant over 4 pi, giving us the energy form of the uncertainty principle. We can actually make a new statement about the uncertainty principle from this derivation. We can say that the more particle-like something is, as indicated by the smallness of its bulge, or delta x, the less wave-like it is, as indicated by the range of wavelengths, or delta p. This helps explain the wave-particle duality in that something cannot be entirely wave-like and entirely particle-like at the same time. Now, I am aware that this is a rather complicated and probably convoluted topic, so I'm going to give you the main points. First off, the Heisenberg uncertainty principle tells us that by merely measuring a particle, we can only know so much about its position and momentum at a given time. It is modeled by the equation delta x times delta p sub x has to be greater than or equal to Planck's constant over 4 pi. There is an equivalent form of the uncertainty principle for energy and time, meaning that we can only know so much about a particle's energy based on how long we measure it. This version is modeled by delta t times delta E has to be greater than or equal to Planck's constant over 4 pi. Everything behaves as both a particle and a wave, and lastly, any quantum mechanical phenomenon, including Heisenberg's uncertainty principle and wave-particle duality, become unnoticeable at large scales due to the mass of everyday objects. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.